Okay, so now we're going to branch off of the cross product a little bit, just do a kind of a little mini lecture on something called the triple scalar product, and we're going to be talking about the volume of a parallelpiped. We'll talk about what a parallelpiped is in just a little bit. So let's suppose that I have an array, and so what an array is it's a collection of numbers or mathematical objects ordered in a rectangular form. And if we have an array of numbers and the array is square, that is that it has the same number of columns as it has rows, then we can perform a calculation using the array called the determinant of the array or the matrix. So let me kind of give you an example here. We actually have already utilized this. I talked a little bit about it, even used the word. The cross product. Let's say we have A cross B. And A cross B, we're going to write it as it's I, J, and K, and then it'll be A1, A2, A3, and B1, B2, B3. Okay? This thing here, it's called an array. Or it could also be called a matrix. Okay, an array or a matrix. And if we kind of put brackets on it, it ends up being a matrix. And so what it is when we find the determinant, actually we utilize the determinant in order to find the cross product. So the determinant ended up being I times these crosses, I times A2 B3 minus B2 A3 minus J times A1 B3 minus B1 A3 plus K times, and then this would be A1 B2 minus A2 B1. Okay? And that actually, this is the determinant of this array. So that's the determinant of the array. So what we do when we find the determinant of an array that is 3 by 3 is we start out with the top left-handmost corner and we multiply it by basically the cross product here, the A2B3 minus B2A3, not the whole cross product, but just that crossing, okay? And then we'll subtract, we'll take the second term and we will basically essentially find our cross product. Okay, or do the multiplication that we use in order to find the cross product, and then plus, and say for example we've got K, and we'll do the same thing as before. We'll basically multiply A1 times B2 minus B1 times A2. So what we can do, that's basically how we go about finding the determinant. So I'm not going to, essentially this is the equation for the determinant. So let's say for example, we'll use an example, is we'll find the determinant. And now we'll do it with 3 vectors. We're going to find the determinant for, and we'll have 1, 0, 1, 2, negative 1, 3, and 0, 1, 4. So the first thing that I'm going to do with that is I'm actually going to go out and I'm going to form an array. And I'm going to write my vectors, okay, along each row. 1, 0, 1, 2, negative 1, 3, and 0, 1, 4. Then I'm going to take, just like in the cross product, I'm now going to take, this is going to equal 1 times, and how we write the determinant is we're going to take the array and we kind of use the absolute value signs. That's actually going to generate, that's our notation for the array. So we'll get that, and then we're going to take 1 times, and it'll be negative 4 minus 3. Okay, because we're basically just going to do that like we did the cross product, plus, or rather, excuse me, minus 0. So we got 0 times, and if you have a 0 there, you don't really have to do anything, but we'll do it anyways. We got 2 times 4 is 8, minus, and then 3, or 8 minus 0, excuse me, because 0 times 3 is 0, plus, and then we have a 1 times, okay, 2 times 1 is 2, and then minus 0, so there's that. Now you'll notice we don't actually end up with a vector here. Instead, we're actually going to end up with a value, like an actual constant value. So we've got negative 7 minus 0 plus 2, so that equals negative 5. So the determinant of this thing, okay, the array made up of my vectors, is equal to negative 5. And so that's the determinant. Let's try it one more time. Okay? We'll find the determinant, and now we'll have A equal to 3, negative 1, 2. B equal to 4, 1, 4. And C equal to 0, negative 1, 2. Write my lines. For my array, 3, negative 1, 2. 4, 1, 4. 0, negative 1, 2. Then I'm going to get 3 times 2 minus negative 4 minus negative 1 times 8 minus 0. Okay, because 4 times 2, 0 times 4, plus 2 times negative 4 minus 0. This ends up giving me 3 times 6, that's 18. And then this is plus 1 times 8, so plus 8 plus negative 8 equals 18, and that's my determinant. And that's how you go about finding the determinant. The reason why the determinant is going to become so handy is because when we talk about the triple scalar product, the way we find the triple scalar product is by finding the determinant. Alright, so let's take a look at this thing called the triple scalar product. And let's suppose that u, v, and w are vectors. And we have the triple scalar product is going to be defined as u dotted with the cross product of v cross w. Okay? And we've seen this before, that this could actually be u cross v dotted with w. It would actually give us the same exact thing. But what's important for us right now for this triple scalar product is to notice that the result, okay, of the triple scalar product is equal to the determinant. So the determinant equals the value from the triple scalar product. Now let's think about this. So the determinant is going to give us back a constant, right? Okay, we know that already. That's what we just saw. And now let's look at what's the result of u dotted with v cross w. Well, in the parentheses we have v cross w, which is a vector. And then we know u is a vector, so we're taking u dotted with another vector. And when we dot those two vectors, we're also going to get a constant. Okay? Now, I'm not going to go into the proof that actually shows that the triple scalar product and the determinant are in fact the same. It's fairly simple. You can look at it instead of your book, okay? Or there's some places online you can take a look at it. But for right now, we're just going to utilize this, okay? I think you can follow it on your own. So let's try it out. So let's take an example. All right? We're going to have u equal to 1, negative 1, 0. We're going to have v equal to 3, 0, negative 2. And we'll have w equal to 2, 1, negative 1. Now, what we'll do is we'll have u, the triple scalar product, u dotted with v cross w, will then equal, and we'll generate our array, 1, negative 1, 0, 3, 0, negative 2, 2, 1, negative 1. And so this gives me 1, right? 1, and then that crossing, so that 1 times essentially 2, because it'll be 0 minus a negative 2, so we'll write that down. 0 minus negative 2, minus negative 1 times negative 3 minus negative 4, plus, and this is 0, so we really don't have to do anything else with it, but we'll do it anyways, 3 minus 0. And so this ends up equaling 2 plus, okay, 2 plus 1, because this is going to end up giving me positive 1. This is going to end up giving me positive 1, so it's 2 plus 1, which equals 3. And that is the value for our triple scalar product for these three vectors. And that's really all you've got to do in order to figure out your triple scalar product. All right, so now let's take a look at the volume of a parallelepiped. And so what we're going to do is we're going to say, okay, let's generate the parallelepiped. So first we've got, let's call this W, and here's V. There's V and W, okay? And then we'll take this is going to be our height U. And we're going to generate a parallelogram using V and W. All right, basically just their addition, they create a parallelogram. And then you kind of imagine, boop, 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 right? And Each one of these is going to be an equivalent vector to u. And so this is essentially our parallelepiped. Is it great? No, it's not perfect. But hey, what are you going to do? Now, any three-dimensional figure that's like a prism, we can find its area, its volume. So the volume is going to be the area of the base times the height. So this base right here, okay, is a parallelogram, right? And we know the area of that parallelogram, this parallelogram right here, okay, is going to equal, so the area of the base equals the cross product of V crossed with W, and it's the magnitude of the cross product, okay? We'll learn that inside of our cross product discussion. In addition to that, we can see as well that if I kind of take a look at this, if we've got V and we've got W, okay, and we take their cross product, we'll get an orthogonal vector to that cross product. Then I want to imagine U is coming up here. So here's U, and here, so here's V, and here's W, and we have the orthogonal vector, right? It's orthogonal to both V and to W, and it is V cross W. My height, the height of the parallelogram, is actually going to be the projection, okay? It's going to be the height projection of U onto V cross W. So my height equals the projection onto V cross W of U. And we learned earlier that what that is that's going to be U dotted with V cross W, okay? Right? The dot product divided by the magnitude of V cross W. Right? That's a formula that we actually learned inside of 2.2, right? When we were working with the dot product. Or 2.3, when we were working with the dot product. So, all we've got to do is now multiply the two together. So my volume, the volume of the parallelepiped, okay, is going to equal V cross W, my base, times U dot V cross W, divided by the magnitude of V cross W, which just means that it's equal to U dotted with V cross W. And there's our volume. So our volume, the volume of this parallelepiped, ends up being the triple scalar product. Sweet. So let's look at an example, just real quick here. We want to find the volume of the parallelepiped generated by these three vectors, A, B, and C. So what that means is that we'll have to have A dotted with, okay, the cross product of B cross C, okay? So that triple scalar product, and we know already that that's going to equal the determinant of the three vectors. So 3, -1, 2, 4, 1, 4, 2, -1, 0. So this ends up equaling 3 times 0 minus a -4 plus, or minus, excuse me, -1 times 4 times 0 minus 8, so -8, plus 2 times, and then we'll take the cross here, that's -4 minus 2, and there's our determinant. And that ends up equaling 12 minus 8 minus 12, which equals -8. Now, it's the volume of the parallelepiped. I should actually add in this, that one thing that we are missing is that this should be actually in absolute value. Okay? We are going to, in fact, for the volume of our parallelepiped, we're going to need to make sure that we keep it all in absolute value so that it's all positive, right? Because it's the volume. So, all right, just make sure that that's the case. Just to add a little piece. So we need to make sure the volume it'll be the absolute value of A cross B cross C. One of the things that's going to be kind of handy for us is we're going to actually be able to utilize this volume of the parallelepiped and thinking about the triple scalar product and the cross product in order to make determinations about some qualities of the vectors that we're looking at. So one of them might be to determine whether or not three vectors are in fact coplanar. So if three vectors are coplanar, what we end up with is that that means that we've got two vectors, and we're going to talk about why two vectors are going to form a plane, right? We've got one vector going this way, we've got second vector going this way, and then what happens if the third vector is actually on the same plane, okay? And if you think about it, and we'll draw a picture in just a moment, if you think about it, what's going to end up happening is that that's actually going to take, we're going to have the parallelogram at the bottom of the parallelepiped, but then, right, when we bring that vector down, it's going to, our vector's going to have no, our parallelepiped's going to have no height. That means it's going to have zero volume, right? And so what that's going to mean for us is that's actually going to mean that if we have three coplanar vectors, it means that the triple scalar product, or the determinant of those three vectors, is actually going to equal 0. All right, so we've got a theorem, and that's the triple scalar product of three coplanar vectors is 0. Now remember that the triple scalar product is the volume of the parallelepiped. Those two things are the same. So let's imagine that I've got two vectors. I've got v and w. Okay, once again, I've got v, I've got w. And now what we're going to do, and we're going to imagine that they generate, okay, that they create this parallelogram, and we're going to have u on the same plane as that parallelogram. Let's say u goes right in through here. Doesn't really matter where it goes, whatever. Now what happens here is notice, okay, the parallelepiped has no height. And since the parallelepiped has no height, the parallelepiped has no volume. So the parallelepiped ends up having no volume. All right, so if we have three coplanar vectors, then the volume of the parallelepiped ends up being 0, and then that means that the triple scalar product of the three coplanar vectors is 0. So if I want to make a determination as to whether or not three vectors are coplanar, what I'm going to do is I'm going to find the determinant, or the triple scalar product, okay, and I'm going to see if it's 0. So let's try that out. So let's determine if A, which is I plus j minus k, B, which is I minus j plus k, and C, which equals I plus j plus k, are coplanar. So what we'll do is we're going to find A dotted with, we're going to find the triple scalar product A dotted with B cross C, and that's the determinant in this case of 1, 1, negative 1, 1, negative 1, 1, and 1, 1, 1. So we'll start out, we're going to get 1 times negative 1 minus 1 plus 1 times 1 minus 1. Or excuse me, this is minus. 1 minus 1 times 1 minus 1 plus negative 1 times 1 minus a negative 1. So if I actually write this out, I get this is going to equal 1 times negative 2 minus 0 plus negative 1 times 2, which equals negative 2 plus negative 2, which equals negative 4. So A, B, and C are not coplanar. Simple. You go out and find the determinant of those three vectors, and we can make, and if the determinant does not equal 0, so if the determinant does not equal 0, then the three vectors are not coplanar. Okay, so this finishes our conversation about the cross product, the triple scalar product, and some of the things that go along with the cross product and triple scalar product. We're going to see a lot more applications of this. We're going to be utilizing it quite a lot. So you want to kind of get comfortable with not only how do we calculate the cross product and the dot product, the triple scalar product, but also what do they mean geometrically? Because it's going to make it a lot easier for you to think through and create connections as we start working more and more with three-dimensional calculus and multi-dimensional calculus.